chapter there where we talked about really empirical formulas and molecular formulas. And before we kind of move on to our next topic, just to remind what we spoke about last time, we talked about really how to calculate both of these, and we did a number of examples of empirical formulas and molecular formulas. So remember that as we talked about, the empirical formula really is the simplest whole number ratio of what's present. So it's that simplest whole number ratio of what's present. While our molecular formula will oftentimes tell us exactly sort of how many of the atoms are present in a particular compound. So remember that, when we calculate the empirical formula, as we talked about last time, there's really sort of a few basic procedures that you want to do. First off, as we talked about, if we're going to calculate it, if you were given the percent composition by mass, as we talked about, you basically can assume 100 grams. 100 grams. And what that basically will do, as we did in a number of examples, is turn our percentages into really just the grams, right? So that allows us to go from percent composition of each of the elements into grams. Then we want to take those grams and we want to convert them into moles. So we would use our molar mass to do that. Once we have all the elements in moles, the next thing we want to do is divide by the smallest number of moles. And once we do that, as we talked about, if we pretty much hit kind of all whole numbers, so for example, let's just say we got A1 and B2, then that would represent our empirical formula. Remember though, if we do sort of the division part and we do not get really a whole number, a number that's not really like right onto that whole number, like a 0.99, 0.98, or just over a whole number like 0.01 or something like that. If we end up dividing, we get something like 1.33 or something like that, or maybe a 2.5 like we talked about. These are numbers where we do have to find a common factor to multiply the empirical formula by to get us to a whole number. So for example, obviously the 2.5, we would want to times the entire empirical formula by 2. So if we had something like 2.5 and B5, we would multiply this empirical formula by 2. That would give us A5, B10 here as sort of our made up empirical formula, and we would end up with obviously whole numbers, and that would be the correct empirical formula, which would then could reduce down. At this point, that would be our empirical formula. To calculate the molecular formula, if we needed to, we pretty much need 3 things. We need the empirical formula. So either you will be given it, you'll follow this sort of procedure here to calculate it. You need the empirical formula's molar mass. And lastly, you need the molar mass of the compound. Out of these 3 things, usually always in textbook problems, that is given to you in the problem. Again, like we saw in a couple of those examples, somewhere along the way, it will say, hey, the apparent molar mass of this compound is 160 grams per mole or something like that. Again, the empirical formula you may have to calculate. You obviously will probably have to calculate the molar mass of that empirical formula as well. What do you do with both of those things? You take the molar mass of the compound and you divide it by the molar mass of the empirical formula, and that will give you a number. So usually this number is pretty close to a whole number, and that is the number that we multiply the empirical formula by to get to our molecular formula. So for example, if we look back at sort of this guy, if that was our empirical formula, we would take it and basically multiply it. Let's just say we got a 2 for this. We would multiply the empirical formula by 2, and that would turn it into A2B4 as our molecular formula in this particular case. So those were the sort of steps that we talked about last time in terms of calculating the empirical formula and really calculating the molecular formula. Obviously, if you were given the molecular formula up front, you could kind of reduce it down. If you could do that by whole numbers, that will get you to your empirical formula. Any questions on the stuff we kind of talked about last time? Remember, we also talked about the idea that you can, if you have the percent compositions of everybody, you can kind of work backwards if you wanted to from the molecular formula to the empirical formula by first calculating the molecular formula by doing the percent composition and using the molar mass of each of the elements and the molar mass of the compound to do that and get the empirical formula. Or you could go from empirical formula to molecular formula. As we talked about last time, in most cases, probably best to go empirical formula to molecular formula. Again, if you maybe mess up a little bit on the percentages or that calculation, a lot of people sometimes get a little bit lost kind of going the opposite way, but you definitely can do it either way. Any questions on any of that stuff there? Okay. So then what we're going to do, that again was basically chapter 5, I think. So we're going to now go backwards to chapter 3, which we pretty much talked about most of chapter 3. We just left one part of chapter 3 left, which is nomenclature. So today we're going to talk about pretty much how to name everything, I guess, that you would ever want, perhaps almost everything that you'd ever want. So nomenclature obviously is a fancy word, right, for naming compounds. And we're really going to talk about two types of compounds, and the two types of compounds that we talked about when we talked about bonding, which was in the beginning part of this chapter. One is ionic, and a reminder that when we deal with ionic compounds, those are usually our metals and non-metals together. And really what we have here, like we talked about in bonding, is we have a transfer of electrons from the metal to the non-metal. So we have that transfer of electrons. That transfer of electrons is going to create a positively charged ion for the metal, a negatively charged anion there for our non-metal. And again, it is these two guys here that are basically no sharing of electrons, but that electrostatic attraction between them, that kind of opposites attract, is what holds that together. So remember, in an ionic bond, absolutely no sharing of electrons, but we have that complete transfer of electrons from the metal to the non-metal. Again, that's why we do result in the metal becoming positively charged and the non-metal becoming negatively charged. And that's different than, say, a covalent bond or a covalent compound or a molecular compound. And that's usually between two nonmetals. And when we have two nonmetals, like we talked about with bonding, here we do have sharing of electrons. And it's that sharing of electrons, which again is basically holding that compound together. As we talked about with bonding, which was in this chapter as well, again, as we know, that sharing of electrons may be equal sharing, which basically creates that non-polar covalent bond. It also may be unequal sharing of electrons, which creates that more sort of polar covalent bond that we see in molecular compounds. These two sort of classes of compounds are really important, and they're also sort of the basis as to how we go about naming everybody, whether or not they're sort of ionic compounds, whether or not they're more molecular compounds, and sharing of electrons happening. So let's take a look at the periodic table just to remind ourselves in terms of charges that we commonly sort of see occur with certain compounds or elements here on the periodic table. Everybody in group 1, which is our lithium, will make a +1 charge. Remember that these guys really don't have charges until they really do start combining, for example, with metals. And that's really where things start to either become positively charged or negatively charged, especially when we're dealing with metals and nonmetals. Group 2 is going to be +2 in that case. When we come over here to group 3, most of the time we're talking about aluminum here. That's going to be +3. Remember, this is our staircase coming down here, and that's where we have our metalloids. And to the upper right of our staircase, that is where we have our nonmetals. So we kind of skip group 4s. There's no real good pattern. Again, you got kind of nonmetals up on top, you got kind of metals below it, and you got the staircase kind of running through. So starting group 5, where our nonmetals are concerned, we go backwards. So we go at -3. Again, because they're nonmetals, they're going to be gaining electrons. Group 6 there is going to be -2, and group 7 will be -1. Other parts in terms of the periodic table are transition metal region, and here, these are the guys that typically have a variable type of charge. And what that means, as we will talk about, is they essentially can, make more than one charge depending on sort of who they are bonded to. For example, copper could be +1, +2. It sort of depends on the situation. Same thing again with like iron and so forth. So they typically have sort of a variety of charges. In addition, some of these guys outside of the transition metal region, in this kind of tin, lead, bismuth, and sort of antimony, in this sort of area of the periodic table as well, although they're not technically in the transition metal region, they are below the staircase, so they will be metals, and they also can have a variety of sort of charges as well. For example, tin could be +2, +4, same thing with lead. So we do run into sort of a similar situation in terms of those charges. We'll talk about obviously how to handle those as we go through it. There is sort of an exception in terms of charges in the transition metal region. There are kind of 3 that have a more fixed sort of charge, and that is zinc and cadmium. And then you kind of hang over here to the left, and silver. So these guys over here, although they are transition metals, they typically do sort of have fixed charges. So when we talk about zinc and cadmium here, they typically are going to be +2 charge. Hanging a left over here to silver, that guy typically is going to be a fixed charge of +1. So those are sort of 3 little exceptions in the transition metal region that, although they are, sort of technically transition metals, they do have more of a fixed charge, and that's sort of how we deal with those when we talk about naming. Any questions on that so far? Again, important to kind of know these charges because it's going to help you obviously put the formulas together correctly when we're dealing with formulas, and also help you naming stuff as well. So let's take a look at sort of the basis. That's another periodic table in case you missed the first one there. So let's talk a little bit about, what does happen in sort of an ionic compound. So obviously in ionic compound, we do create ions. And ions, as we've talked about, are really things that have charges. So they're charged entities. And we basically have 2 types of ions. We have the cation, which is positively charged. And that is a result of, as we just sort of saw there a second ago, really metals that lose electrons, right? So obviously, if something loses electrons, it now has more protons than electrons, becomes positively charged. Anions, on the other hand, are ones that are negatively charged. And in the case, they are typically going to be our nonmetal that's going to pick up the electron there and is going to gain an electron, 1 electron, maybe 2 electrons, however many electrons it gains. And how do we go about if you just had perhaps just the formula of just either a cation or an anion? How do we go about naming them? Well, naming the cations are pretty straightforward. If we want to name something that is just a cation, we essentially just use the whole name of the metal. So for example, if we had K plus, K is potassium, it's group 1, which is why it makes a +1 charge. And if that was just the formula of the cation we had, we would just call it the whole name there, which is potassium, and it would be referred to as an ion usually at the end. We have H plus. H, which is not necessarily a metal, it's a non-metal, but it is sometimes treated kind of similar to metals in terms of naming. We would call this the hydrogen ion. If we had something like barium, which is group 2, that would be our barium ion. If we had something like silver here with a +1 charge, again, it would be the silver ion here. What about our anions? Well, our anions, in terms of naming our anions, what we typically do with this is sort of use the root there of the non-metal name, and the ending part gets changed to IDE at the end. So we kind of drop the last part of that non-metal name. We can insert our IDE there, and that's about how we would name anions. So if we had O2 minus, oxygen being group number 6 would have a -2 charge. Oxygen becomes the oxide, IDE ion. Nitrogen with a -3 charge. We drop the last part there of nitrogen, or a little bit more than that maybe. And this becomes the nitride, IDE ion. Br minus, which is bromine, again, dropping that last part there, becomes bromide, IDE ion. Hydrogen, which is an unusual guy, also can in certain cases be negative as well. We sometimes see the negative version here, and that would be known as hydride, IDE at the end of it, ion. So hydrogen is sort of the only one that can sort of go both ways, if you will, positive or negative. Hydrogen typically will be negative if it comes after a metal in an ionic compound, as we'll talk about there. So if you just simply have just the ion by itself, either the cation, which is positively charged, or the anion, which is negatively charged, again, cation, whole name of the metal, and anion, IDE at the end of it. Any questions on that there? Okay, so let's get into then, sort of how we come about are talking about here naming ionic compounds. We basically are going to kind of put these guys together. So as we talked about, we will start with ionic compounds first. And ionic compounds, a couple of things. They are going to involve, obviously, the metal and non-metal like we've talked about. But a couple important things here is in terms of the formula for an ionic compound. Whenever we put the formula sort of together, we always want to make sure that we end up with no charge on the formula. So if we write the formula for an ionic compound, we want to end up with really an overall charge of 0. So for example, if we take a sodium ion and we want to put it together with a chloride ion, this one's not bad, right? We have a +1 charge here, got a -1 charge here. So obviously we just need one of each, would give us NaCl. When we do write the formula for an ionic compound such as this, we do not include charges. So there's absolutely no charges being written in the formula, although it does represent basically two things that do have charges. So it does represent, obviously, the sodium ion. So we have one of these sodium ions here that has a +1 charge, and also one Cl that has a -1 charge. So although we don't write the actual charges in the ionic compounds formula when we put them together, it does represent really two things that do have charges, obviously. And again, that's because this is a metal and a non-metal together. Obviously, this was, pretty straightforward. If we got something like our calcium and we put it together with a fluoride. Again, if we put it together just straight one-to-one relationship here, we would end up with CaF+, which obviously has a charge, which we cannot do. So again, when we put it together, we want to make sure that, we do end up with no charge. What you should be able to obviously see is we need not one F minuses, but we do need two of them in this case to balance it out. That gives us a grand total of +2 for our positives, gives us a grand total of -2 there for our negative guys. That gives us our formula CaF2. Again, the formula when it comes together in our ionic compound has no charge associated with it, but it does represent, again, just like in the first example, we have basically one calcium, and that calcium has a +2 charge. It has two of these fluorides, and each one has a -1 charge for a grand total of -2 in this particular case. So whenever we put together ionic compounds, they're always put together in the simplest whole number ratios. And that may sound familiar from what we were just talking about at the very beginning here. That means that that is really an empirical formula. So when we talk about sort of ionic compounds are essentially empirical formulas because when we put them together in the simplest whole number ratios that will essentially give us no charge. Any questions on that there? We also talked about, when we talked about bonding, why this really is, right? And if you remember, when we talked about bonding in this chapter or a little bit ago, what is really the purpose of why we need, two of these guys? Why do we need to balance out the charges? And if you remember, if we were to draw our Lewis structure, Lewis dot symbol there for calcium, it's got two valence electrons. If we drew it for our fluorine, it is group 7, which means it has really not 7 valence electron, 9 total, but 7 valence. And as we talked about, what's going to happen, right, is the calcium's going to lose an electron over to the first fluorine, and he's full at that point, right? He's going to then become fluorine with, that extra electron and that negative charge. That's good for that fluorine, but bad for the calcium, right? Because he's trying to achieve that noble gas configuration like we talked about, right? And he needs to lose up that extra electron. So in order to do that, again, we need that extra fluorine there to allow it to pick it up. And really the sort of the basis of kind of putting these guys together in that simplest whole number ratio is, in the case of sort of ionic compounds like this, it allows everybody really to sort of achieve that kind of group 8 noble gas configuration. And we want to do that obviously in the simplest way to achieve that. And as you can see here by sort of drawing it, that is the simplest way to do that. We pretty much just need those two fluorines to pick up the electrons, both of the electrons for calcium, to allow calcium to reach back to argon's configuration. Question on that there? Okay. Here's a table, kind of what we've been talking about. Again, if we simply just have the formula of an ion, if it's a positive ion, pretty much just the name of the element. A lot of times we will, kind of throw ion at the end of it. If you have something with a negative, as we talked about earlier, kind of keep the beginning part, and then we kind of drop the IDE in there. So we have our fluoride. Important, if you're asked to write the formula of a cation or an anion, because they are ions, you do need to make sure you include the charges. So if you come across a question where you're not asked to write the formula of an ionic compound, but you're just asked to write what is the formula of the cation that makes it up perhaps, or the anion that makes it up, when you write those formulas, because they are ions, you do need to make sure you include the charges. Again, you don't include the charges when you put them together, the cation and anion, but you always want to write the charges when you write them separately here. In terms of when we do put them together, there's always sort of an order at which you want to put them together, and we'll talk about that right now. Let's talk about the first type of ionic compounds. These guys are sometimes referred to as type 1 compounds, and type 1 compounds is really an ionic compound where, as we've been talking about, our transfer of electrons going to happen from our metal and non-metal. And whenever you have a metal and a non-metal together, the most important part of that situation is really always the metal. So it's always the metal that's, sort of the important part of that combination. And in the case of type 1 compounds, when we talk about the metal here comes from group 1 on the periodic table, group 2 on the periodic table, group 3 on the periodic table, or it may be silver, zinc, or cadmium. And what does all these guys really have sort of in common? What they all have in common is they all have a fixed positive charge. So if you remember, everybody in group 1 is +1, everybody in group 2 is +2, everybody in group 3 is +3. So they all have a fixed positive charge, including our silver, which again is +1, our zinc is +2, and our cadmium is +2 as well. So when we have a metal and non-metal, and when you can identify the metal as being from group 1, 2, or 3, or that zinc, cadmium, or silver, it would be basically classified as a type 1 compound. And what happens is we would use the whole name of the metal. And then our non-metal will get the same ending that we were just talking about. We will drop the last part there of our non-metal, and we will insert the IDE. Now, as I just mentioned, there is an order to which we write formulas. There's an order to which we write the names of these guys, which are ionic, and it is always metal, then non-metal, or cation first, followed by the anion. And that goes both for the formula when you write it and also when you name it. So that's sort of the order at which you want to always write these sort of formulas. For sometimes some people like to put the negative guy first and then the positive, but it should always go positive, then negative, metal, then non-metal, or really cation, then anion. So if we look at something like what we had there, NaCl, again, if we were to analyze this, we want to first look at our first guy there and go, Na is a metal, Cl is a non-metal. So this is an ionic compound. First off, again, looking at the metal, which is the important guy, that is going to tell us that is group 1. That means he has a fixed charge. That means it's type 1. And at this point, you pretty much don't have to worry about anything else here. You pretty much just use the whole name of our first one, which is sodium. The chlorine then becomes chloride. So this would be obviously sodium chloride. Again, the formula here for the compound has no charges. It is made up of a cation that is positively 1 charged, and it's made up of an anion, which is negatively 1 charged. Any questions on that particular one there? Now, if we look at another one like CaBr2, here again, if we were to sort of analyze this, what we want to look at is I see Ca, which is a metal. I see Br, which is a non-metal. Again, the metal is going to be my important one to look at. I see calcium, which is from group 2 on the periodic table. It means it has a fixed charge. That means, again, it's going to be type 1, which means I proceed to the whole name of it, which is calcium. Second guy, which is our non-metal here, is going to become bromide. So this would be calcium bromide if you follow those. Now, let's talk about something that people very commonly like to do in this situation. And that is, I got a 2 here. I think this name would be much better if it was like calcium dibromide, because there's a 2 di. Seems like we should do that. And let me just tell you, you should not do that. So this number here, in the case of type 1, will have no effect on the name. You could have 42 of them there. You probably won't, but you could. And it would still be called bromide. So we do not use any type of prefix here at all in type 1. And again, that's a very common thing that people always want to kind of use the prefixes everywhere and everywhere. We will very shortly talk about where you should use the prefixes, but this is not the situation for you to use the prefix. So this should be calcium bromide in that case. Any questions on that? Now, again, calcium bromide here, the formula does not have a charge, but it is made up of really 2 ions. One is calcium, which is group 2, which would be our cation. And one is Br minus, which would be our anion here. And this is why we actually do have the 2 here in the formula. It is because when we put this together, we got a +2 for the calcium. We have a -1 for the Br minus there. That means we truly need 1 more there to balance out the -2 charge. And that's where the 2 is. So you need that 2 in the formula, but has no effect here on the name. And you would just call this calcium bromide. Question on that there. So again, people oftentimes have that urge to sort of use those prefixes in every single naming sort of aspect. But you want to make sure that you only use it in the appropriate place. And again, that is not here. Any questions on type 1? Again, here's that little chart that we just kind of went over there on the first one of our common sort of charges, or our fixed charges. Again, you can kind of add zinc and cadmium in here, and silver as well. And if as soon as you kind of see anybody in terms of the metal part, which is the important part, being there in that compound, type 1, and again, we got that fixed charge happening. All right, so why don't we take a look at some here, give you a chance to try a few. So for each of these on the left-hand side, why don't you take a couple minutes and why don't you write the correct name? Let me actually give you some names and see if you could write the formulas. So let me try calcium nitride. Let's go with aluminum oxide. Let's do potassium phosphide. And why don't we do, that looks good, I think. That should be good, I think. All right, left-hand side, let's go with proper names. Take a few minutes. Right-hand side, proper formulas. So take a minute or 2 here, and then we'll talk about it, make sure everybody's on the same page. Which is a non-metal. Again, it is the metal that's the most important guy here, and we know potassium is group number 1, which means it would be K+, which would be the cation. We know Cl is group 7, which would be Cl-, which is our anion here. But really, again, just knowing the potassium part of it, which is group 1, means we could proceed right to the name here and use the whole name of the metal, which is potassium. And Cl goes from chlorine to chloride, IDE at the end, and we get potassium chloride. Any questions on that one there? Continuing down then, we got Zn as Zn, which is zinc, which is a metal. S, which is sulfur, which is a non-metal. Again, it's going to be our metal that's important. Here, though, it's not part of group 1, 2, or 3, but it is one of those transition metals that have a fixed charge, and it does have a fixed charge of a +2, and that would be our cation. The S here has a fixed charge of -2, as it is group number 6 on the periodic table, and that would be our anion. So since the zinc here does have a fixed charge, we could proceed to the whole name of the metal, and again, our non-metal going to get the IDE at the end of it, and that would be zinc sulfide. Any questions on that one there? Okay, so since we did our calcium bromide earlier, we'll change it out to MgS. Same thing here, Mg, which is group number 2, and that is a fixed charge of magnesium with a +2 charge, which would be our cation. S, just like above, is still S2-, which is our anion. But again, it is the magnesium. That's the important part. Since it has that fixed charge from group number 2, we would use the whole name here of our metal. So this is magnesium. Sulfur, just like above, becomes sulfide. And lastly here, if we kind of look at the last one, we got Ba, which is barium. Again, that's group 2, which means really that's as far as you need to go in terms of your analysis. But we will continue here and think about the rest of it. We actually have barium, which would be our cation here with a +2 charge. We actually have hydrogen here coming after a metal. This case, this hydrogen is actually -1 charged here, and it is the anion. So again, when hydrogen comes second in the formula after a metal, it will carry that negative charge. We again really name it off of the barium. So since the barium is group 2, has that fixed charge, it would be barium, and this would be hydride. Again, no need for a dye or anything on that because of the 2. The 2 is there to balance out the charge. Again, we need 2 of them there to balance out the charge of barium. Any questions on going from formula to name here? Okay, then let's talk about going the other way, which is also really important to be able to do. Going the other way, really, when you're putting a formula together, you really just want to think about the basic 2 units that make it up and obviously put it together so you get no charge. So when we see calcium, calcium is group number 2, which means really we have a calcium with a +2 charge. Nitride is nitrogen on the periodic table. Nitrogen is group 5, which would have a -3 charge. So again, when we put that together, we have a +2 and a -3. The common number between that is 6. To get calcium to 6, we need 3 of them. And what that basically says is we have 1, 2, and 3 calciums. To get nitrogen to 6 there, or nitride to 6, we need 2 of them, which basically tells us we have 2 of these guys. -6, +6, everybody's balanced, and everybody is happy on that one there. Question on that? Now, sometimes people will tell you you could just do the crossover move. And if you do it in this case, bring the 3 down, bring the 2 over to the other side and down, you will get the right formula. But, it's important to really know how to properly sort of do this and balance it, because I will warn you that the crossover move, I don't know, I haven't measured it, but, maybe 92% accurate, I suppose, most of the time, does not work 100% of the time to get you the correct formula, just so you know. You could also, sometimes people go the opposite way. If you have the formula go kind of up and up, it works a lot of times, but it doesn't work 100% of the time to give you the correct formula in every situation. So if you just do it kind of blindly, you will find yourself with some wrong formulas along the way. So again, it's best to think about these things in terms of balancing them rather than just blindly crossing things over in terms of charges and stuff like that. Or if you're happy with 90-ish% of the time, then you can just blindly do it. You'll be okay. But again, sometimes people do it that way, or sometimes you have the formula, people will kind of go this way and this way to try to figure out the charges. And again, like I said, more times than not, you'll be okay. But there are some times when you will not be okay. So just keep that in mind. If you are going to blindly kind of cross things over, you might actually get a few wrong along the way. Here again, we look at aluminum and oxide, which is oxygen, aluminum being group 3 +3 charge, oxygen being group 6 there, -2 charge. Same sort of thing here. Basically, common number there is 6. You literally could just draw them out if you're not sure and count up how many you got on each side. So obviously here I need 2 aluminums. And I need 3 oxygens here to balance it out. And that would give me the correct formula. And lastly here, potassium phosphide. Potassium, which is group 1, is a +1 charge. Phosphide there, which is group number 5, is a -3 charge. Again, same idea here. We're taking a +1 and a -3. We definitely need more of the potassium, right? So we need 3 of them total. Gives us K3P in terms of the formula. Question on going from name to formula. Again, it's good to kind of keep it simple. Think about just the basic units of what make those guys up and put them together. Any questions on that one there? So this is a type 1 ionic compound. What makes it type 1 is the metal, which is the important part. Metal has a fixed charge. Simply put, you use the whole name of the metal, IDE on that non-metal. Again, don't throw in any extras there. Sometimes extras are not good, like prefixes and stuff like that in this situation. All right, so let's then talk about the other type of ionic compound, and this is what is sometimes referred to as a type 2 compound. Type 2 compound, very much like a type 1 compound, is a metal and non-metal, and just like before, we're going to get some electrons being transferred, and just like before, it is the metal that is the most important sort of part of this. That is going to be a metal that comes from our transition metal region. Are just to the right on the periodic table. And we're talking about kind of under the staircase. The staircase we're talking about is the metalloid sort of staircase. Remember, on the periodic table above is nonmetals. Below the staircase are metals. So some of these metals in that sort of area, metals like tin, lead, bismuth, antimony, these guys, although they're again not classified really as transition metals, what they share in common with transition metals is they have the ability to have a variable charge. And again, in certain situations, the same element can have multiple types of charges that are happening. Something, again, as I mentioned earlier, copper could be +1 in certain situations. Copper could be +2 in other situations. Iron could be +2. Iron could be +3 in certain situations. Lead 4, for example. So because they really have this sort of variable in terms of their charge, what is naming? Naming is really just telling people, what you're dealing with. So we do have to sort of indicate that to the person that's reading the name or looking at the name. So how do we go about naming these is pretty much identical to type 1. We're still going to use the whole name of the metal, which will come first. We're still going to use the non-metal, and we're going to give it the IDE treatment at the end. The additional thing that we put in there is a Roman numeral. So we do include a Roman numeral with these guys. What does the Roman numeral mean? And this is oftentimes misunderstood by students, the Roman numeral. The Roman numeral is actually the charge, the positive charge on the metal, not the grand total charge of all the metals, not how many metals you have. The Roman numeral is the charge, the positive charge really, on the metal. So basically what that means is if you took one of the metals out all by itself, what the charge of it would be, what the positive charge on that one metal would actually be. So if we had just the ions by itself, like say Cu plus, and we wanted to give the name of this, this would be the copper Roman numeral 1 ion, right? If we had Cu2 plus, it would be copper Roman numeral 2 ion. Roman numeral 1 because it has a +1 charge. Roman numeral 2 because it has a +2 charge. Again, not how many we have. So if we had something, for example, like FeCl2, we would analyze this kind of the same way as we did the previous one. We would look at it and go, I see iron, which is a metal. I see Cl, which is a non-metal. So I want to look and see really where that metal is located. So the metal is obviously, in this case, a transition metal. And as soon as you see that transition metal in a formula or something like that, you should think of type 2. You also should think, I need a Roman numeral. What that really means is, for example, you may not know right off the bat what the charge is on the iron. The good news is you will always know what the charge is on what's attached to the metal. So in this case, we have Cl. Cl is group 7. So we know that group 7 has a -1 charge. Again, here, there's not just one of them, but there are two of them. So if we just simply add those together, that means sort of the overall negative charge that we have going on here is -2. Remember, this is an ionic compound. It's a positive guy and negative guy. So obviously when we put them together, we still are shooting for no charge overall. So to make it no charge, since there's only one iron present, it would have to have a +2 charge in this case. And that would give us a name of whole name of the metal, Roman numeral 2 here, because again, not how many we have, but the actual charge that we have on the metal. And just like in type 1, even though there are two of them there, it has no effect on the name. We still call it chloride. Again, not dichloride, but just chloride here. And this would be iron Roman numeral 2 chloride would be the proper name for this particular guy here. Question on that there? Why is that important? Well, what happens if we had this guy, FeCl3? Again, if we sort of analyze it the same way, iron still our transition metal, not really sure what the charge might be. Cl still our non-metal, which is -1, but in this case, we actually have not two of them, but we have three of them, which means we got a grand total of -3. In this particular situation, even though they're both iron and chlorine together, in this particular situation, the iron actually is carrying a +3 charge, which means it should have iron Roman numeral 3, and again, chloride here in terms of the name. And again, the name is really just telling people, you know, in this particular case, what you are dealing with in terms of the charge on the metal. Any questions on that there? So metal, non-metal, metal always the important one. Here, the metal going to have a variable charge because it is a transition metal just to the right of it, and we do need to take it into account. Yeah, so in terms, Ryan, in terms of knowing by looking at the periodic table, the different charges, let's actually look at it here. In terms of just by looking at the periodic table to answer your question, and metals, really the ones we sort of talked about a minute ago or a little bit earlier, these are the ones you really will know sort of the charges for sure. The guys in group 1, which is +1, the ones in group 2, which is +2, that's our aluminum, which is +3. And then these guys right here, these kind of guys that have fixed charges. Now, when you're dealing kind of in your transition metal region, which is, kind of in obviously this range. And again, a little bit underneath that staircase outside of it, you really can't just look at it and go, okay, it's iron, so it's always going to be +2, or it's iron is going to always be +3. It really does depend on sort of what it is bound to in terms of figuring out the charge. So that's why you sort of want to work your way backwards, kind of like what we did in those other two examples. The good news, like I said, is you'll always know, for example, something like this, you'll always know what the charge is on what it's bound to, especially if it's a transition metal or something. And again, this, for example, is Cl minus because it's group 7. That means that this would has to be the +1 in this situation. And this would be copper, Roman numeral 1, chloride. So in terms of sort of type 1 metals, you will know the charge of it because it should be group 1, group 2, or group 3, or that zinc, cadmium, silver, which do have that sort of fixed charge. But in terms of sort of transition metals, are again in that sort of lead or tin area, you do have to take a moment and sort of look at it in the formula and figure out, sort of what the charge would be on it. The only way you would actually know the charge on say a transition metal or type 2 metal is actually if you were given the name, for example, if we were given copper 1 chloride and you're kind of working backwards into the formula, the copper Roman numeral 1 tells you that it is a copper with a +1 charge. So kind of going backwards from the name to the formula, if you see the Roman numeral, you'll definitely know what the charge is. But kind of going from the formula to the name in terms of a type 2 metal, you do have to sort of figure it out. Other questions on that? Now, while we're talking about these sort of type 2 guys, there is one that's sort of a different one that you might think, and that's mercury. So there's mercury +2, 2, and then there's mercury +2. And you may think to yourself, well, the guy with all the 2s should be mercury 2, and it's actually not. It says mercury 1. And that's because it comes sort of as a dimer, kind of 2 +1s together, hooked together. This guy with less 2s is actually mercury 2. So that's kind of an unusual one that sometimes confuses people. It does kind of make sense. You would think the one with all the 2s would probably be mercury 2, but it's actually mercury 1. So that's one that sometimes throws people off. But again, transition metal, to the right of the transition metals, you do need to sort of work through sort of what it's bound to, so you know what the positive charge is on that metal in that particular compound. And Roman numeral is needed here to indicate the individual charge of a metal. Any questions on that one there? How does this one, though, while we're kind of talking about mercury here, how does this one sort of represent itself in, say, a formula or something like that? How could you maybe tell one versus the other? If you had something like HG2O and maybe like HGO, the 2 here from like mercury 1 gets sort of incorporated in there as well. And again, this would be like mercury 1 oxide. This would be mercury 2 oxide here. Again, it doesn't have that extra 2 there. So that little 2 there does kind of hang out, obviously, as you get into the actual formulas as well. Now, slide got a little bit messed up, so I apologize about that. But there's a slide from your book here, but it does tell us sort of our Roman numeral says here, and really the purpose of this slide as well was to show you there's sort of an older way of naming sort of type 2 compounds. And for example, something like iron, where it can have Fe2 plus and Fe3 plus. Obviously, we would call this the iron 2 ion, the iron 3 ion. Sometimes, you know, it may be called the ferric or the ferrous ion. And again, it's sort of an older way of naming it, like cupric and cuprous for copper, and copper 2, copper 1, and copper 2, cupric and cuprous. And this kind of older way of naming, we really won't use. We'll use obviously the Roman numeral way here, and most people use sort of the Roman numeral approach. But kind of just to give you a hint as to sort of how this works, the one with the OUS is usually the smaller positive charge. The one that ends in IC is usually the larger positive charge. So if you look at Fe3 plus versus Fe2 plus, ferric versus ferrous, and same thing here, Cu2 plus would be cupric and Cu plus would be cuprous. You could also see they don't use sort of our normal names that we use, more of the origin type names that are sometimes used as well. You occasionally sometimes see those kind of older way of naming pop up as well still. So it's good to sort of remember it. But for us, we will use strictly more the Roman numeral type of way. Any questions on that there? Okay. So why don't we try some here and see how we do. So just like before, why don't we do some names of the guys on the left, and why don't we add one? Let's go with PbO2. And why don't we do some names as well? And we'll do some chromium 3 chloride. Let's do some nickel 4 oxide. Let's do some bismuth 3 nitride. All right, take a few minutes and see what you come up with on that. Okay, let us take a look and see how we're doing here. Starting with the first one here, we'll take a look. We got CO, which is cobalt. We got Cl, which is chlorine. So we have the metal, non-metal. Again, our metal going to be the important one. If you look at the metal dead center there in the transition metal region, number 27, that automatically tells us that it's type 2. Automatically should tell you, not quite sure maybe what the charge is on it. But as we talked about, you will know what the charge is on and what it's bound to. So this is Cl. This is group number 7. And that means it has a -1 charge. And there's 3 of them, which basically means you got this deal happening. That's a grand total of -3. That means in this case, to balance it out to 0, cobalt's got to be +3. And that gives you cobalt Roman numeral 3. Remember, the Roman numeral is not how many you have, but the actual positive charge you got going on there. Just like previously, even though there's a 3 and even though you wanted to use that try, don't do it. It is just chloride. So this is cobalt Roman numeral 3 chloride. Any questions on that one there? Going down to the next one, Cu, which is copper, also a transition metal. I, which is iodine, which is a non-metal. Again, copper being that transition metal, automatically tells you it's type 2, automatically tells you can have multiple types of charges. We know that I is group number 7, which means it has a -1 charge. So to balance that out, we obviously will just need a +1 charge on the copper. This would be copper Roman numeral 1. Again, for the charge we got going on there, iodine becomes iodide in this case, and that would be copper 1 iodide. Any question on that one there? Coming this way, we got SN. That's our good friend 10. 10, not necessarily a transition metal, but it's number 50 there on the periodic table, I think. And that is just to the right of the transition metals. So even though it's not, it is kind of named the same way. It means it can have multiple types of charges. Could be +2, could be +4, or some other things. We look at Br, which is our non-metal, group 7, and it is -1. And again, if you need to, just keep it simple. Just write out what it says. There's 4 of these. So that's a grand total of -4. That means that's a +4. That means that's a 10 Roman numeral 4. Again, for the charge, even though we got 4 of these BRs, still only going to be called bromide at the end here. Lastly, we look at PB, which is lead, not a transition metal, but to the right, lucky number 82 there, also can have multiple type charges, sort of variable charges. So again, we're going to take the same approach here and go, all right, oxygen, which is group 6, is -2, and there's 2 of them. That gives us a -4, which means the lead here is actually +4, not +2. And this would be lead Roman numeral 4 oxide because of the charge. Now, on that particular one, I say not to, because if you just blindly did the crossover move like we were talking about, you would end up with lead 2 and oxygen -1, which both are incorrect in this case, and might have led you to lead 2 Roman numeral, and it would be wrong. So this is a case where crossing over will not get you the right answer. So as I mentioned before, works in a lot of cases, doesn't work 100% of the time. So again, best just to kind of think about it like this: how many negatives, how many positives, and kind of put it together that way. Again, will not always get you the right answer. I can't tell you how many people will very commonly write lead 2 oxide on this, or lead 2 dioxide, though sometimes write as well, which is wrong. But because of that, because they just kind of blindly do the switch over move and they end up with the wrong formula. Any question on any of those names there? Okay. Then obviously let's go backwards. And as I was just mentioning just a moment ago, you know, this is sort of the one place where you can sort of know what the charge is on a metal, is sort of going from name back to formula. So again, when it says here chromium Roman numeral 3, what that means is the chromium has a +3 charge, kind of going backwards. So that tells us automatically what the charge is. By the way, as soon as I see that Roman numeral, I know it's a type 2 kind of transition metal guy happening. Chloride is chlorine, which is group 7, which is -1. Again, now we want to put this together to get us no charge. And really to do that, we need a grand total of 3 of these guys. And that gives us CrCl3 in this case. Any questions on that one? Looking at the nickel 4, again with the Roman numeral, that tells us we have a nickel with a +4 charge. Oxide is oxygen, which is group 2. Not group 2, it is group 6 that has a -2 charge. When we put these guys together, we actually need 1 more of those oxygens there to balance it out. And in this case, we will end up with NiO2 would be the proper formula. Again, here, if you did the crossover move where you did the nickel and the oxygen and you went boom and boom, and you went, okay, Ni2 O4. This would be incorrect. Although it is balanced, it is not the simplest way of doing that. You could reduce this down to 1 and 2, which is the right way of doing it. Because remember, these ionic compounds are empirical formulas, so the simplest way to do it. So again, a situation if you kind of blindly just did the crossover move, you would not get the right formula. Question on that there. Lastly here, bismuth, Roman numeral 3 means we have a Bi with a +3. Nitride, which is group 5, is -3. So this one's pretty straightforward. Just need one of each of those guys, and we will end up with the right formula there. Any questions on that one? Any questions on type 1 or type 2 ionic compounds? They both are metals and nonmetals. They both do not have any sharing of electrons. They are both made up of cations and anions. Difference is type 1, no Roman numeral. Type 2, Roman numeral. Any questions on that? Yeah. So then let's talk about, here's sort of a decision tree as to which way to go. Again, type 1, name a cation using the element name, determine the charge, and include a Roman numeral for type 2. Let's talk about polyatomic ions. And polyatomic ions are really groups of nonmetals that are together through really covalent bonding, but have a charge overall. So polyatomic ions are really these kind of groups of nonmetals that have charges and special names. So let's take a look at one here. Let's say we had NH4NO3. NH4NO3 is actually 2 polyatomic ions. We would split it right about there. And on this side of it, we have probably one of the only positive polyatomic ions you'll come across, which is NH4+. What does that mean? Well, that one nitrogen and those 4 hydrogens, they're all bonded together. They're all actually sharing electrons here because they're all nonmetals, and they move around as one whole unit. That entire whole unit has a +1 charge, and it has a special name, which is known as the ammonium ion. That NO3 is also a polyatomic ion. It is NO3-. Same thing here, that one nitrogen and those 3 oxygens. They absolutely stay together because they're sharing electrons. They don't break apart, and they move around as one unit and has an overall charge of -1. And that is the nitrate ion. So how do we do this? Well, in this case, since we have 2 polyatomic ions, if we needed to name the top guy there, it would be known as ammonium nitrate. Why is the formula like it is here? It is like that because ultimately we're putting something together that has a +1 charge with something together that has a -1 charge. That means we essentially just need one of each of them. So we just slap it all together into this formula here. Questions on that? Just to sort of tie it into bonding and what we talked about before, we've actually drawn the Lewis structure for this guy, I think. NH4+ looks like this when we draw it. Those nitrogens, hydrogens are all sharing electrons. Overall thing has a +1 charge. Nitrate, we also have drawn the Lewis structure, I think, along the way. Looks something like this. Overall guy here has a -1 charge. Again, there are sharing of electrons happening here in our polyatomic ions. We got some sharing electrons here. which is why this entire thing moves as a unit. We also have sharing of electrons here, which is why this entire thing moves as one unit. So sometimes when people are dealing with polyatomic ions, they have that urge of, I want to break it up into all the individual parts, like NH4 plus moves into like nitrogen by itself, some hydrogens by itself, and they don't, because they are bonded together like so. They move as one whole unit as they're moving around. And again, they have the appropriate charge, really kind of based like on formal charge and stuff like that we talked about with bonding. You know, overall, this guy's carrying a kind of +1 charge. Overall, this guy's carrying a -1 charge. So we really just need one of each of those. And that's really what this formula here basically represents. Any questions on that there? So what's the deal with polyatomic ions? Well, I'll be honest with you, we're going to see a chart here in just a second, but in most cases, polyatomic ions are negatively charged. So most of the time, these guys are going to carry a negative charge. So what does that mean? It means probably 9 times out of 10, if you come across a polyatomic ion, it's probably hooked up with a metal. Metal acting as the positive guy, the polyatomic ion, in a lot of cases acting as the negative guy. So what does that mean? Well, when you have a metal and a polyatomic ion that come together, we basically follow our type 1, our type 2 rules, which means whenever the metal's involved, it's always the most important thing. So if you have a metal that's a type 1 metal, you do not need a Roman numeral. So if you had something like NaNO3, that is sodium, type 1. That is nitrate. This is called sodium nitrate. No Roman numeral, just like we would do if it was like sodium chloride or something like that, right? Now, if we had, say, CuNO3, Cu is a transition metal. That is a copper, which I'm not sure what the charge is, but I do know that the charge on the nitrate is -1, right? Which means in this case, the copper to balance it out must be +1. And this would be copper Roman numeral 1, just like we did for type 2. And again, instead of doing the IDE, we just use the whole name of the polyatomic ion. And this becomes copper Roman numeral 1 nitrate. So most of the time, our polyatomic ions are probably going to be hooked up with a metal. We do follow that sort of metal rule. If it needs a Roman numeral, put it in. If it doesn't, then don't. But basically, we do the type 1, type 2, and then the whole name of the polyatomic ion. Any questions on that there? Bad news time is this is the table, or a table, of all the different polyatomic ions. And you do have to just kind of memorize them. By the way, if this is wrong, that 4 should be on the bottom. So this should be NH4 plus. So fix that up there. So that's NH4 plus, which is ammonium. There's some other ones through here, but what's the best way to sort of approach this table? You do need to know the names. You do need to know the charges, because that's going to help you really kind of name things. So if we look on this table, for example, we will see things like NO3 minus, which again, as we've been talking about, has a -1 charge. You also see something like NO2 minus, which is 1 nitrogen and 2 oxygens all together, also with a -1 charge. Only difference on these two guys is the number of oxygens. This guy, again, is nitrate, the nitrate ion. This guy is nitrite ion. If you look over, there's SO4 2 minus, 1 sulfur, 4 oxygens, has a -2 charge. SO3 2 minus, 1 sulfur, 3 oxygens, has a -2 charge. And that is going to be sulfate, and this would be sulfite. When you're dealing with polyatomic ions in a group of two, for example, like these guys, the one that has the most oxygen in a group of two will end in 8. So these guys have the most oxygen in these groups of two. They end in 8. The one with the least number of oxygens in a group of two will end in 8. So that's a good way to learn these, is to kind of group them together. The one with the most oxygens will usually end in 8. The one with the least number of oxygens will end in 8. Now, there's other things that we see on this table. For example, if we take CO3 2 minus, that's 1 carbon, 3 oxygens, all bound together. We've drawn carbonate, by the way. We've drawn everybody here, Lewis structures. This is carbonate. Sometimes we may add an H plus to that and get HCO3 minus. Again, we added the hydrogen, which is why the hydrogen went on, but we also added a plus to a minus 2, leaves us a minus 1. What did we add to that? We added basically hydrogen. So this is sometimes referred to as hydrogen carbonate. And because it's chemistry and they like to, mess with you, I suppose, sometimes people don't call it hydrogen, but they do call it bicarbonate. The bi instead of the hydrogen here. Also, bisulfate is another example that comes across as well. I think we should have that somewhere here, maybe bisulfate. Maybe not, right there. So bisulfate, also another example of that. Another common thing that we have are actually groups of 4 that are related to each other. So right here, and in a group of 4, we basically have ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. Every single one of these have a -1 charge. And if we break this kind of group of 4 up right about there, to the left are guys that have the most oxygen. And if we look at their names here, the one with the second most oxygen ends in 8, and it's known as chlorate. We can't name the guy with the most oxygens the same, so it also ends with 8, but it starts with per. So this ClO4 minus is perchlorate. This is chlorate. These two guys on the right have the least number of oxygens. They should end in ite, which they do. So they both end in ite. So this is chlorite, this guy right here. But the one with the least number of oxygens in a group of 4, in addition to starting with ite or ending with ite, they start with hypo. So that's hypochlorite, hypochlorite, chlorite, chlorate, and perchlorate. You also see a similar pattern here because Cl is a halogen. You can swap it out for Br, which is also a halogen. Works the same way. Hypobromite, bromite, bromate, and perbromate. You could also swap it out with another halogen over here in a group of 4 with the iodine, and you get periodate, iodate, and iodite, and so forth going through there. So groups of 4, a lot of them have those halogens in it. And again, the 2 with the most oxygens ends in 8. 2 with the least number of oxygens end in ite. Now, a good way sometimes people will remember these is they may just go, all right, I'm just going to remember all the 8s. And I know the ites will just be 1 oxygen less. So that's a good way sometimes to remember these. Remember all the 8s. And if you need the ite, just take away an oxygen, or vice versa, remember all the ites. And if you need an 8, you add 1 oxygen to it. Charge doesn't change. So that's a good way to kind of group them together. A vast majority of our polyatomic ions here do end in 8 or ite, but there also are some polyatomic ions that end in IDE. So for example, OH minus is hydroxide, IDE. We also have N3 minus, which is azide, IDE. O2 minus, peroxide, ends in IDE. But a vast majority of our polyatomic ions will end in either H or ite, but there are a few that do end in IDE, like those few there. Question on sort of the polyatomic ions there.